For those of you who have been in the JavaScript community for a while, it's like very hard to introduce Lin Clark just because she's been in the community for a while. But if you have ever heard of code cartoons, or if you ever heard of WebAssembly, or if you are even remotely interested in this new thing called Rust that apparently everyone is like super excited about, Lin is truly a person you should have seen before. But if you haven't, aren't you in luck? Because she's here today, which is great. So without further ado, I'm just going to give it up for Lin, and please do the same.
Thank you all. So hi, I am Lin Clark, and I make code cartoons. And I also work at Mozilla, where I get to work on things like WebAssembly, which is what I'll be talking about today. So first off, what is WebAssembly? WebAssembly is a way of running code that's not JavaScript on the web. So up until now, if you wanted to run code on a web page to do something like change the page in reaction to an event or something like that, run a calculation, the only language that you could use was JavaScript. But now there's WebAssembly, and you can use other languages like C or C++ or Rust on the web page too. And I wish I had time to go into all of the details of how that works under the hood, because it's really fascinating. But unfortunately, this talk is so jam-packed with the future, I don't have time to talk too much about what's currently in browsers. And I actually don't have enough time to really talk in detail about everything that's in the talk. But I did write a blog post that's on this subject as well. You can go to the Hacks blog that was published in October and look for the WebAssembly's post MVP Future blog post if you want more detail. So once you get to Hacks, you can also look at old posts that I've done on WebAssembly. My first articles about WebAssembly came out when WebAssembly was first turned on by default in browsers, and you might have seen those. Since then, though, I've noticed that some people have a misconception about WebAssembly. They think that the MVP that was turned on by default in browsers in 2017 is the final version of WebAssembly. And I can understand where that misconception comes from, because the WebAssembly CG is really committed to backwards compatibility. So the WebAssembly that you write today is going to continue working long into the future. But that doesn't mean that it's feature complete. And in fact, that's far from the case. Features are coming to WebAssembly that will fundamentally alter what you can do with WebAssembly. I think of these future features kind of like the skill tree in a video game. We've fully filled in the top few of those features, of those skills, but there's still this whole skill tree below that we need to fill in to unlock all of the applications that WebAssembly can address. So let's look at what's been filled in already, and then we can see what is yet to come. So WebAssembly's story starts with Emscripten, which made it possible to bring large existing C and C++ code bases to the web, so for things like games and desktop apps. And it did this by transpiling the C or C++ to JavaScript. But that JavaScript that it automatically generated was still significantly slower than the native code version. A stroke of insight fixed this, though. One of Firefox's JavaScript engineers figured out that you could actually optimize the JavaScript engine to understand what was going on there, to understand types and stuff like that. And it could optimize this code really well. And that gave us Asm.js. Once the other browser vendors saw how fast Asm.js could go, they started adding the same optimizations to their engines. But that wasn't the end of the story. It was just the beginning of this story. There were still things that engines could do to make this run even faster. But they couldn't do that in JavaScript itself. Instead, they needed a new language, one that was designed specifically to be compiled to, and that is WebAssembly. So what skills were needed for the first version of WebAssembly to get to this minimum viable product that could run C and C++ on the web? Well, WebAssembly's designers knew that eventually they'd want to support more than just C and C++, so they needed a language-agnostic compile target. Something like the assembly language that desktop apps are compiled to, something like x86. But this assembly language wouldn't actually be for a physical machine. It would be for a conceptual machine. The compiler target also had to run code very fast to meet users' expectations for smooth interactions and gameplay. And it needed to load fast, too, because web users are really used to having these kind of immediate load times, not downloading these huge executables before they run them. But these kinds of applications that we're bringing to the web, those are pretty big code bases. And that means there's a lot to download and compile when your user first goes to the URL. So we needed our compile target to be compact, and that way it could go over the internet quickly. These languages also needed to use memory differently than JS uses memory. They needed to be able to go dive into the bytes directly, because languages like C and C++ have a language feature called pointers, where you actually have a memory address that you can read and write from. But you can't have a program that you're downloading from the web just being able to access your memory willy-nilly. So in order to provide a way to access memory like a native application is used to, but keep the browser secure, we had to create something that could give access to a very limited part of the memory, a specific part of the memory, and nothing else. To do this, WebAssembly uses a linear memory model. So this is just implemented using a feature called typed arrays, just JavaScript arrays, really. Except the array only contains bytes of memory. So when you're accessing it, you're just using array indexes, but you can treat them as if they were memory addresses. And this means that you can pretend that this array is C++ memory. So with all of these things in place, you could run desktop applications and games in your browser as if they were running natively on your machine. And that was pretty much it. That was the skill set that WebAssembly had when it was released as an MVP. It truly was an MVP, a minimum viable product. It allowed certain kinds of applications to work, but there are still a whole host of other applications that these features don't fully address. So let's look at some of these other achievements that we have to unlock. The next achievement to unlock is heavier weight applications. Can you imagine if something like Photoshop were running in your browser? Just like Gmail, you could load it across a bunch of different devices instantaneously and start working on your files? We've already started seeing things like this. For example, the AutoCAD team has brought their CAD software available in the browser, and Adobe has made Lightroom available through the browser using WebAssembly. But there are still a few features that we need to make sure that all of these applications, even the heaviest of heavyweight applications, can run well in the browser. So first is support for multi-threading. Modern day computers have multiple cores that can process things in parallel. But to make use of those cores, you need support for threading. There's another bit of modern hardware that processes things in parallel, and that's SIMD, single instruction multiple data. So with SIMD, it's possible to take a chunk of memory and split it up across different execution units, which are kind of like cores. And then you have that the same bit of code, the same instruction, running across all of these different execution units, but they're working on different data. Another hardware capability is 64-bit addressing. So memory addresses are just numbers. So if you have a memory address that only has 32 bits, it's only 32 bits long, you can only have so many memory addresses. You only have enough numbers for about 4 gigabytes. But most modern hardware supports 64-bit addressing, which offers 16 exabytes of memory addresses. And of course, that's a big difference. So adding 64-bit support will take the artificial limitation out of WebAssembly. But these applications don't just need to run fast. Load times need to be fast too. One big step here is to do streaming compilation. So this is where you compile the file as it's being downloaded. And WebAssembly was designed for this. We did this in Firefox. We actually compile the file so fast as it's coming down that basically once you finish downloading, it's almost instantaneously compiled. It just has to do that little last bit before it's done. And other browsers are adding streaming to their compilers as well. Tiering your compiler also helps. So in Firefox, we actually have 2 compilers. The first one's called the baseline compiler, and that kicks in immediately. That's that one that's streaming and getting your file compiled really quickly so you have a fast load time. Then another compiler, the optimizing compiler, comes in, and it runs in the background on several threads. So this is while your code's actually already starting to execute. It's running in the background. And this one takes longer to compile, but it generates extremely fast code. And so when it's done, it will swap that out with the baseline version will be swapped out with the optimized version. And we're also actually working on a new optimizing compiler called CraneLift at Mozilla. It's designed to compile code quickly. It can compile code in parallel at the function by function level. So very, very granular parallelism. But the code it generates is still very fast. So what we're hoping is that we'll have even faster compile time and faster generated code with this. And there's an even better trick that we can use to skip compiling most of the time. Unlike JS, if you load the same WebAssembly file twice, it compiles to the same machine code. So that means that we can actually store that compiled code in the HTTP cache. And while the page is loading, when it goes to fetch the page, to fetch that WASM file, the cache will give it the precompiled version of the code. And so this will skip compiling completely if this is already in your cache. And there are other ways to skip even more work. So stay tuned to see what else happens to improve these load times. Where are we with supporting these heavyweight applications right now? For threading, we have a proposal that's pretty much done, but a key piece of that, shared array buffers, had to be turned off in browsers early last year because of the Spectre security issue, but they will be turned on again soon. SIMD is under very active development at the moment. For WASM64, we have a good picture of how it will work, and that's pretty similar to how x86 and ARM got support for 64-bit addressing. For streaming compilation, we added our streaming compiler last year, and other browsers are also working on their streaming compiler implementations. We also added our baseline compiler, and a couple of the other engines are adding baseline compilers. In Firefox, HTTP caching is almost there. And these other improvements are in discussion, in early discussions. Even though this is all still in progress, heavyweight desktop applications are already coming to the browser today, because WebAssembly already gives a lot of these applications the performance that they need. But once these features are all in place, once these skills are there, this is going to be another achievement unlocked. And more of these heavyweight applications are going to be able to come to the browser. But WebAssembly isn't just about desktop applications. It's also meant for regular web development, for the kind of small modules web development that you're used to. If you have a module that does a lot of heavy processing, a lot of computation, that's a good candidate for switching over to WebAssembly. And again, we're already seeing some of this. So the parser in the source maps library that's used in Firefox DevTools and Webpack, they changed their parser to be written in Rust that compiles to WebAssembly. And that's now 11 times faster than it was before. And the Gutenberg parser in WordPress is now an average of 86 times faster. But for this to go mainstream, for this kind of development, the small modules WebAssembly development to go mainstream, we need a few more things in place. So first, calls between JavaScript and WebAssembly need to be fast. But when WebAssembly came out, these calls weren't fast because engines needed to optimize them. They hadn't done it yet because it was an MVP. We finished our work on this in Firefox last summer, and now some of these calls are actually faster than JavaScript to JavaScript calls unless they've been inlined. That brings us to another thing, though. You often need to pass data between your JavaScript and WebAssembly functions. So you need to pass arguments into your WebAssembly function and return values from it. And this can be slow, and it can be difficult too. The reason for this is because at the moment, WebAssembly only understands numbers. This means that you can't pass more complex things like objects into WebAssembly as parameters. You need to actually take that object, turn it into a number representation in the linear memory, and then take it back out on the other side and figure out what it means. And that's kind of complicated. And it takes some time to actually do that conversion as well. So we need this to be easier and faster. We also need to integrate with ES modules. So right now, you can't import and export with WebAssembly modules. And that means that WebAssembly won't be part of your JavaScript graph if you're not importing and exporting them. Just being able to import and export doesn't get us all of the way there, though. We also need ways to distribute and bundle these modules. So what is the NPM for WebAssembly? Well, what about NPM? What's the Webpack or parcel for WebAssembly? How about Webpack and parcel? These modules shouldn't look any different to the people that are using them, so there's no need to create a whole other ecosystem for them. And there's one more thing that we need. support for older versions of browsers, even those that don't know what WebAssembly is, like IE 11. So where are we on all of this? Well, calls between JavaScript and WebAssembly are fast in Firefox now, and other browsers are prioritizing this. For easy and fast data exchange, there are a few proposals that will help with this. The reference types proposal makes it possible to use references as arguments and return values. And these references, they refer to objects that WebAssembly doesn't know about, so like a JavaScript object. And another proposal, the host bindings proposal, will actually make this, so that's going to be pretty fast to start with. The host bindings proposal will make it even faster. And another thing that we can make easier in this process is dealing with memory. Because right now, if you have some data that's in the linear memory that WebAssembly put there that JavaScript needs to access, whenever the JavaScript's done with accessing it, it needs to go in and free that memory. It needs to actually clear out that part of linear memory that's not needed anymore. But with weak refs, there will be a way to automate this. So these proposals are all in flight. In the meantime, the Rust ecosystem has created tools that handle this well for Rust code. For ES module integration, there's a proposal that's pretty far along. For toolchain support, there are tools like WasmPack in the Rust ecosystem, which automatically runs a bunch of tools for you and packages up your code for NPM. And the bundlers are also actively working on support for loading WebAssembly modules. Finally, for backwards compatibility, there's the WASM2.js tool. And that takes your WASM file and spits out the equivalent JavaScript. And this JavaScript's not going to run fast, but at least it's going to work in old versions of browsers like IE 11. Once we unlock this achievement, we also unlock the path to another two. And that's rewriting parts of JavaScript frameworks in WebAssembly and making it possible for statically typed compile-to-JS languages to compile to WebAssembly instead. So these are languages like Scala.js or Reason or Elm. For both of these use cases, WebAssembly needs support for high-level language features. So first, let's look at what it would be for rewriting parts of JavaScript frameworks. For a framework like React, you could parallelize the virtual DOM differing algorithm using something like Rust that has really ergonomic support for parallelization. And you could also speed things up by reduce memory usage by allocating memory differently during that process of diffing. But you would still need to interact with JavaScript objects, things like components, from that code. You wouldn't just want to write everything to linear memory because that's difficult and inefficient. So you need to be able to have things in WebAssembly pointing to JavaScript objects, things in JavaScript objects pointing to linear memory. And sometimes that would possibly create cycles. And that can spell trouble for the garbage collector. So WebAssembly needs integration with GC, with the browser's garbage collector, to make sure that these kinds of cross-language data dependencies actually can work. And this will also help languages that compile to JavaScript, like Scala.js, Reason, or Elm. These languages use JavaScript's garbage collector when they compile to JS. And that's the same garbage collector that WebAssembly that's running in the browser will use. So they won't need to change their GC. And I said WebAssembly that's running in the browser because this garbage collection proposal is not adding the browser's garbage collector to the WebAssembly spec. It's just allowing you to plug in the host to plug in a garbage collector. So the browser, in the browser, they'll be using the browser's garbage collector. But other host environments will be able to bring their own garbage collection if they want to as well. We also need better support for handling exceptions. Most WebAssembly modules currently don't support exception handling. But JavaScript does have exceptions. So even if you've compiled your code not to use exceptions, JS may throw one into the works. And then if your WebAssembly function calls a JS function that throws, your WebAssembly module likely won't be able to actually handle that exception. So we need to make this work better. We also need good debugging support. Dev tools in browsers make it really easy to step through JavaScript. We need the same for WebAssembly. And finally, for many functional languages, you need to have support for something called tail calls. So where are we on these? For garbage collection, there are two proposals currently underway, the typed objects proposal for JavaScript and the GC proposal for WebAssembly. And our team actually already has a prototype of these working, but it will take some time for these to go through standardization. So we're probably looking at sometime next year. Exception handling is still in the research and development phase. For debugging, there's currently some support in browser dev tools, but it's still not ideal. So there's a subgroup of the WebAssembly CG that's working on specifying that. And the tail calls proposal is also underway. Once those are all in place, we'll have unlocked JavaScript frameworks and many compiled to JS languages. So those are the achievements that we can unlock inside of the browser. But what about outside of the browser? Now, you may be confused when I talk about outside of the browser, because isn't the browser what we use to view the web? And isn't the web right in the name, WebAssembly? But the truth is, technologies like HTML and CSS and JavaScript are only part of what makes the web. They're the visible part. They're what you see. They're what you use to create a user interface. So they're the most obvious part of the web. But there's another really important part of the web which has properties which aren't as visible. That is the link. The link's innovation is that I can point a link to your page without having to put it in a central registry or ask you or even know who you are. And it's this ease of linking that enabled us to form these global communities of people we didn't know. But there are two problems that we haven't addressed with just this link. So the first one is, you go visit a site and it delivers some code to you. How does it know what kind of code it should deliver to you? Because if you're running on a Mac or if you're running on Windows, you're going to need different kinds of machine code. So does a website need to have a different version of the code for every possible device? No. Instead, the site has one version of the code, the source code, and that's what's delivered to the user. And then that's translated to machine code on the user's device. The name for this concept is portability. With it, websites don't need to know what kind of device you're running. But that brings us to a second problem. If you don't know these people whose web pages you're loading, how do you know what kind of code they're giving you? It could be trying to take over your system. Doesn't this vision of the web, where you run code from anybody whose link you follow, mean that you have to blindly trust anyone who's on the web? This is where the other key concept from the web comes in. That's the security model. So basically, the browser takes the code that is downloaded and puts it in a sandbox. And it puts a couple of toys in those sandbox so that it can do some fun things. But it doesn't put any dangerous toys in there, things like being able to directly write to files. The utility of the link on the web is based on these two things. It's based on having this portability, being able to deliver the source code, the same code, to every device and have it run. And the sandbox, this security model that lets you run code without putting your system at risk. So what difference does it make if you think about the web this way? Well, it changes the way that you think about WebAssembly. You can think about WebAssembly as just another tool in the browser's toolbox, which it is. But it's not just that. WebAssembly also gives us a way to take these other two capabilities of the web, the portability and the security model, and bring them to other use cases that need them too, so that we can expand the boundaries of the web past the boundaries of the browser. Now, you may be thinking this already happened with Node.js. But as it is today, Node doesn't quite get us there. It doesn't give us full portability. And it also doesn't give us the same security, the same confidence to run untrusted code. So with Node, it's possible to run JavaScript on servers and other devices without a browser. So that gives you some portability. But you still need native modules, as Francisco was saying earlier today. You still need native modules if you really need that performance. So you might need it because you need performance. You might also need it because you already have an existing C or C++ code base that you want to reuse. But these native modules aren't portable. They have to be compiled specifically for the user's device ahead of time. We're also still missing security. Node could have taken the sandbox from the browser, but Node made the design decision early that JS modules would have full access to system APIs. So JS modules can do things like write and read files on your machine. So these capabilities, things like direct file access, are the dangerous toys that the browser doesn't make available. Even though they're dangerous, for the kinds of use cases that Node addresses, this kind of access does make a certain kind of sense. The thing I want to make clear here, though, is that Node made a choice. And it's really that Node had a choice to make when it comes to JavaScript. For JavaScript modules, it could have gone with a sandbox-style approach, where it didn't allow these modules to have access to the dangerous toys. But for native modules, Node had less of a choice, because it's actually pretty hard to sandbox native code. Now for Node, this is really a moot point. These design decisions are baked into the ecosystem, and if you're running a Node application on your computer, then you're basically saying, I trust this code. But what about other use cases? Wouldn't it be nice to have both the portability and the security of the web? WebAssembly makes this possible. It starts with these advantages of JavaScript, the portability and ability to be sandboxed that you see in the browser. And what it adds is performance. So that means that developers don't have to resort to unsandboxed native code to get that performance. So we can bring the portability and security to use cases outside the web, to use cases from the cloud to the blockchain to the Internet of Things. And I'll talk more about how we can do this in a second. But first I want to finish up with Node. Because even though Node has no use for WebAssembly's ability to run untrusted code, WebAssembly can still help Node. So how can we improve Node with WebAssembly? Well, we could bring full portability to Node. We could eliminate most of the need for native modules, ones that are compiled ahead of time for the user's device. And these could be written in WebAssembly instead and just compiled once by the developer. And then these modules could run across all devices, just like JS modules. The only problem here is that WebAssembly doesn't have direct access to the system's resources. That's part of the point. So we need to pass in functions so that it could work with the operating system, so it could write files and read files and things like that. For Node, this will probably include a lot of the functionality that you see in things like the C standard library and things that are part of POSIX, which is the Portable Operating System Interface. And that's an older standard that it helps with compatibility across Unix-like operating systems. To make this happen, the Node core folks would need to figure out what API they want to use for these functions. But wouldn't it be nice if that were actually something that were standardized? Not something that was constrained just to Node, but that could also be used across other runtimes and use cases too. If we had this standard interface, a POSIX for WebAssembly, if you will, a POSIX, a portable WebAssembly system interface. And if that were done in the right way, you could even implement the same API, but in a different way for the web. Now, these functions wouldn't be part of the WebAssembly spec necessarily. They could be part of a different spec in the WebAssembly CG. They could be part of a spec outside the WebAssembly CG. And there would be WASM hosts that wouldn't have them available. But for those platforms that could make use of them, there would be a unified API for calling these functions, no matter which platform the code was running on. And this would make universal modules, ones that run across both Node and the web, so much easier. So is this something that could actually happen? Well, a few things are working in this idea's favor. There's a proposal called the Package Name Maps proposal, and this will provide a mechanism for mapping a module name to a path to load the module from. And that'll likely be supported both by browsers and Node. So that'll make it possible to provide different paths and load entirely different modules, but with the same API. With that mechanism in place, what's left to do is actually figure out those functions that make sense, which functions make sense for Node, and what should their interface be. Now, there are a lot of discussions that are heading in this direction right now, and it looks very likely to happen in one form or another. And I think this is actually coming pretty soon, which is good, because unlocking this gets us halfway to unlocking some other use cases outside of the browser. And with this in place, we can accelerate the pace. So what are some examples of these other use cases? One of them is things like CDNs and serverless and edge computing. CDNs want to be able to run code instead of just delivering static resources as they've traditionally done. So with this, they're getting as complex as servers, but CDNs work at a different scale. While a regular server might serve hundreds or thousands of requests per second, CDNs, you're talking about tens of thousands of requests per second. And you're actually already seeing this with one of the CDNs already has WebAssembly running. It's Fastly, and this allows them to run user code at a scale that regular servers can't. How they do this is fascinating. So I recommend watching their CTO, Tyler McMullen, talk about it. But the point is that WebAssembly gives them the safety, speed, and scale that they need for this use case. So what did they need to do to make this work? They needed to create their own runtime, which means taking a WebAssembly compiler, so something that can turn WebAssembly into machine code, and combining it with these functions that I was just talking about, the standard library ones where you can then interact with the system from that code. For the WebAssembly compiler, they use the one that we're working on at Mozilla called CraneLift. Unfortunately, the developer of CraneLift is here with us today, so if you have questions about that, he can answer them. And CraneLift is very fast and doesn't use much memory. Now, for the functions that interact with the rest of the world, the system, they had to create their own, because we don't have that portable interface available yet. So it's possible to create your own runtime today, but it takes a bit of work. It takes some design work. And that's effort that's going to have to be duplicated across different companies if everybody has to build their own runtime. What if we didn't just have the portable interface, but we also had a common runtime that could be used across all of these companies and other use cases? So that would definitely speed up development. It would mean that we could address these use cases faster. Because other companies could just use that runtime, like you would Node today if you're doing something with JavaScript, instead of creating your own from scratch. So what is the status of this? Even though there's no standard runtime yet, there are a few runtime projects in flight now. There's one called WAVM, which is built on top of LLVM, and there's one called WASMJIT. And we are actually working on one that's built on top of CraneLift. It's called WASMTime. And if you want to get involved with it, feel free to talk to me later. The developer who's working on CraneLift is also working on WASMTime, so he can also help people figure out how that works. One thing that I forgot to mention about why WebAssembly is useful for things like serverless and edge computing is when you're running on someone else's server, they need to figure out how much to charge you. They need to figure out how many CPU cycles you used. Now, some people call this fuel, how much fuel you used, but that fuel can be hard to calculate because if different programs are running simultaneously on the same server, on the same machine, you can't really tell which one is using it accurately very easily. But since WebAssembly is pretty close to actual assembly, it makes it easier to see how much fuel something is going to use. Another use case that uses this concept of fuel or gas is the blockchain. So unfortunately, I don't have enough time to explain the blockchain, both because this talk is short and because the blockchain is really hard to explain. But there are some versions of the blockchain that can really benefit from WebAssembly. So in Ethereum, there are these bits of code called smart contracts, and anyone can write a smart contract. And then other people called miners have to run this smart contract on their machines. So this should sound a little familiar. It's that same untrusted code problem that we talked about before. Up until now, Ethereum has dealt with this by having their own language, which restricts what the code can do. But that's a pretty high-level language, and it was hard to calculate how much gas or how many cycles that executing that code was going to use. And it also meant that you had to learn this language to write a smart contract. WebAssembly they're currently moving over to WebAssembly, and it's a good option for them because it gives them security, it makes it easier to calculate the gas costs, and it opens up smart contracts to all of these other languages. These blockchain platforms are almost like a new kind of operating system. But WebAssembly can also be used in more traditional operating systems. Now, to be clear, I'm not talking about the kernel, which brave souls are trying, but WebAssembly running in Ring 3 mode, in user mode. Then you could do things like having portable CLI tools that could be used across all different kinds of operating systems. And this is pretty close to another use case too, the Internet of Things. So that includes things like wearable technology and smart home appliances. These things are often really resource constrained. They don't pack much computing power, and they don't have much memory. And this is exactly the kind of situation where a compiler like CraneLift and a runtime like WASMtime could shine, because they would be efficient and low memory. And there are so many of them that are very slightly different, and WebAssembly's portability would really help with that. So that's one more place where WebAssembly has a future. Now let's zoom back out and look at the skill tree. I said at the beginning of the talk that people have this misconception about WebAssembly. They had this idea that the version of WebAssembly that landed in the MVP was the final version of WebAssembly. I think you can see now why this is a misconception. Yes, the MVP did open up a lot of opportunities, and it made it possible to bring desktop applications and games to the web. But we still have many use cases to unlock, from heavyweight desktop applications to small modules to JS frameworks, and to all of those things outside of the browser, things like Node and serverless in the blockchain and the Internet of Things. So the WebAssembly that we have today is not the end of the story, because WebAssembly still has promise to keep and many places to go before it sleeps. Now, before I finish up, I just want to give a little bit of thanks. I really enjoy working at Mozilla because I get to work on really exciting projects like WebAssembly, but I also enjoy it because I get to work with some of the most interesting, innovative, smartest people that I have ever had the chance, and kindest people that I've ever had the chance to work with. And I had a chance to collaborate with two of them on this talk. So Luke Wagner, who is one of the co-creators of Asm.js and was a major driving force in making WebAssembly happen, and Till Schneidereit, who leads our WebAssembly developer tooling efforts at Mozilla. So thank you to both of them, and thank you all for listening.
Let's go straight into the Q&A. Oh man, a question all the way back. Will I run over there? I guess so. Okay. Okay, here we go. Here we go.
And I may ask Dan Goman, the developer of CraneLift and WASMtime, to help me on some of these questions.
Well, I hope it's going to be worth it since you had to walk all the way here. Well, thanks for your presentation. So I was just curious, how do you think sort of the browser will be redefined in the future with new browsers like Brave that use sort of blockchain technology and decentralized applications? From your point of view, sort of where you see sort of like new use cases emerging in how we use the browser? Maybe you know, since you work at Mozilla.
New use cases and how we use the browser. I have to admit, I was not prepared for that question. I think that a lot of the new use cases for the browser, you might actually see, so I know that Brave's doing some experimental stuff in the browser itself, but I think that one of the nice things about WebAssembly is that it makes it possible to ship things outside that aren't part of the browser's code base itself that still perform almost as if they were part of the browser's code base, that they're fast enough. And so that actually, I think, leaves it open for the ecosystem to create lots of interesting new browser features, rather than having the browser developers have to bake these features into the browser itself. So I think that we're going to see a lot of innovation happening in the ecosystem as a result of WebAssembly.
Can you sketch out what POSIX is going to have in it, like roughly?
This is something where I would defer to Dan Goman.
So we're currently working on a proposal. Okay, we're currently working on a proposal. POSIX, if you take the whole thing, is a very, very large API with lots of surface area, lots of details and everything. And we don't think we want to expose necessarily all that. We don't just want to drop POSIX on all the platforms and say you have to implement the entire thing. And so we're working on a proposal to sort of carve out what we think is a meaningful POSIX-like API, which will support existing applications in a meaningful way with enough functionality to be useful, and not too much to sort of overwhelm implementers in the first round. So we're kind of still working on that proposal, and we're going to have something up pretty soon.
What are the core pieces? Like file systems, network access?
File systems, network access, being the two biggies. Also, timers, AP clocks, APIs, random numbers. But basically, files and networking are the sort of two core areas we're looking at right now.
Whoops. Sorry. Here.
Yeah. Your 3-year, 5-year prediction. C++ takes over JavaScript in the browser world?
Well, I should disclose my bias here because I do work at Mozilla and we work on Rust. But I actually think that even if I didn't work at Mozilla, I would say that Rust, I think, is the best candidate at the moment for taking over a lot of the current applications for web applications. Because the Rust community is doing a really good job of creating tools that work with the existing JavaScript ecosystem. So I think that right now, C and C++, when you're compiling for the web, you're generally actually compiling full applications that are all written in C and C++. Rust is really trying to target these small module applications as well.
It might be a little similar question. Do you see a situation where people would start misusing, or maybe that is what we should do, like writing your whole web app in WASM because people think that will be faster even for like super basic stuff you could write in JavaScript?
I think you always have that. You know, people using React when they shouldn't use React, when they don't really need React. You always have people saying, oh, it's the fastest, I'm going to use that, even if their specific application doesn't really require that. And I mean, sometimes there may be use cases where if you have a simple enough app, it actually is a little slower. So I think that this really gets to the point that Francisca made earlier today about make sure that you're benchmarking, you're figuring out exactly what you want to optimize and why you want to use WebAssembly before assuming that it'll just make everything fast.
As someone who tried that, I can also tell you that like my bad Rust is apparently sometimes slower than good JavaScript. It turns out if you don't actually know what Rust is.
Yeah.
I'm wondering if you could speak a little bit more about integration between WASM and the graphics pipeline, particularly in terms of things like GL and just the entire idea of going directly to the graphics and maybe also integrating CSS while you do it, or maybe drop it all together. I mean, what does that kind of three-way thing look like?
As far as I'm aware, there aren't actually plans to directly. I don't know, Dan, do you know? Okay. I don't know of any plans to circumvent anything in between WebAssembly and the graphics pipeline. The idea with WebAssembly is it runs in the same engine and basically has a lot of the same APIs available to it. And that way you make sure that you're not opening up new security holes and stuff like that that aren't already part of the engine. That just makes it, because a lot of the engines have been really hardened over time. The JavaScript engines have been really hardened over time. And so we're taking advantage of that hardening.
As part of using all these tools, you have to generally go through different layers. Like you have to go to, in web workers, and you can go into WASM, and then you might, in Electron, you might go into different processes. And like sort of the difficulty is like object marshalling and how do you transparently go between the layers. And in some situations, just as, like especially message passing, it's really rough, right? It'd be much nicer to just call a method and then just transparently go through all the layers. Are there any projects that are sort of set up to do that?
So let me make sure I got the question correctly. You specifically are interested in data marshaling between WebAssembly and what was?
Well, any boundaries. So like if you're like a post message, imagine you want to make like 100,000 calls.
Yeah.
Constantly writing that code would be ugly.
So if you are using post message, and that's the way you're doing things, if you're posting messages, WebAssembly, that's kind of orthogonal to WebAssembly, but with threading and shared array buffers, you can use shared state, shared memory, and basically not have to do the post message stuff. But there's nothing that is happening in WebAssembly to make something like post message work better, as far as I'm aware. Dan? Okay.
There are a lot of existing native apps, both desktop and mobile, where I'd really like to be able to just drop in some WebAssembly code. You know, like not JavaScript at all, but I just want to reuse this essentially portable code. Mm-hmm. Is that a use case for WebAssembly, and is that something I can do now?
Yeah, so you said in a native module or a native app you would want to do that?
Like an iOS app, I just want to drop in a WebAssembly file from a CDN.
Yeah. To be honest, I actually don't know enough about iOS development to know how feasible that is. But you can definitely have WebAssembly without JavaScript. And so it is something that I think would be possible.
All right. Well, once again, thank you so much, Lin.